Welcome to the Falling Walls plenary table, Advances in Fusion Technology, Breakthrough in Unlimited Energy Generation.
Hello everyone, and welcome to our session on fusion energy. Welcome not only to the people here in the audience today, but also to the people watching online. I'm Dr. Melanie Windridge. I'm a plasma physicist by background, and I'm CEO of Fusion Energy Insights. We help people keep up to date with developments in the growing fusion industry. Now, maybe you're wondering, but what is fusion energy? Well, fusion is the reaction that powers the sun and the stars, and scientists are working to harness it on Earth as a clean source of energy. It's very potent. Just 1 kilogram of fusion fuel releases as much energy as 10 million kilograms of fossil fuels. It produces no greenhouse gases, no long-lived radioactive waste, and it would provide a source of non-variable electricity and the potential for other applications, such as heat for industry or producing hydrogen for synthetic fuels, or even, perhaps, for space propulsion in the future. It's an exciting time for fusion at the moment, as we're starting to see an increase in private companies and the transition from science in the laboratories out into the commercial space. And so these are some of the things that we want to discuss today, some of the advances in fusion. So I'm delighted to have with me a very eminent panel. I'm going to introduce them to you now. First of all, we have Konstantin Hefner, the Managing Director of the Fraunhofer Institute for Laser Technology. Welcome. Can we have a round of applause, please? Take a seat. Thank you. And we have Peter Leibinger, Chief Technology Officer of Trumpf. Thank you. Tim Luce, Chief Scientist at ITER. Thank you. And we have Vinod Philip, member of the Executive Board of Siemens Energy. Take a seat here. Thank you. Sorry, I'm confusing you by standing at the front. Thank you all for being with us today. So let's start off, first of all, by thinking about fusion and the changes in fusion in recent years, because we're starting to see it discussed more in the news, maybe about technological advances or investment. And people in the past have sometimes seen it as a technology for the future, as science fiction. Maybe you've seen it in films like Spider-Man. And what has been happening recently? I'm going to go to all of you. What has been happening recently? What advances have been happening that have changed the outlook for fusion, have made it not so much science fiction anymore? Can we start with Tim?
So for us, especially at the ITER project, we've begun assembly. So it's no longer a paper study, it's no longer fabrication, it's actually putting the thing together to make it work.
Tell us quickly, what is the ITER project?
So ITER is a group of 7 members, because the EU isn't a nation in a sense, but it's 7 members who've joined together to realize magnetic fusion energy for electricity or any kind of energy production. Our goal is 500 megawatts of power sustained with a gain of 10.
Thank you. So you were saying that on the ITER side, the advances have been that you're actually building, you're actually constructing ITER, so you're getting closer to the time when you will actually be doing the experiments.
But also there have been advances in experiments at the laboratory scale. For example, the JET tokamak in Cullum, UK, has just sustained fusion power above 10 megawatts for as long as they could with the technology they had. So it was a demonstration of what was learned in the 90s. It's been improved upon. The predictions were close to true, so it gives us some confidence that the predictability of large devices is there now.
Mm-hmm. So you have confidence for the future? Thank you. Berthold, what advances have you seen that have changed your outlook for fusion?
Yeah, I think there are two sides to it. So one is on the technology side, things have changed, and I'll come to that in a second. But I think the other side is also what we see from the market side. And when you look at the energy world as we do, the thing that we're looking for is trying to manage the triangle. It's a trilemma between sustainable energy, reliable or secure energy, and affordable energy. And as the world is looking more and more towards a net zero future, it is becoming increasingly evident that it is going to be a multi-technology play, and something like nuclear fusion is going to be almost necessary to be able to meet this triangle of needs. At the same time, I think from the technology perspective, in addition to what Tim just said, there are a lot of advances, and I'm sure Peter will talk a bit more about it from his background, but advanced manufacturing technologies, material science, the way we can now create nanostructures that we couldn't do before. I think a lot of these adjacencies are coming together and converging to a point where things that were considered to be really far out and fiction are now becoming more and more real, and the demand side is also growing for that.
Thank you. So our capabilities are increasing as well. Konstantin.
Yeah, I think the main change that we've seen in this long story of fusion energy that has come for the last 50 years is we have a burning plasma platform now. And so this is a massive change because it indicates basically that we're moving from a science problem into an engineering problem. There's still a lot of problems to solve, of course, but we have now physics proof that it does work in the laboratory, and that's a massive change. And I think the other thing that you alluded to was on the MFE side, we're getting to machines now that are actually at full scale. Full scale means they can achieve ignition. And so we have two platforms now, IFE, ICF, and MFE, both at the scale of achieving fusion energy with net gain. And so I think that is a change.
Thank you. So, yeah, we're going to come to, in a minute, the differences between inertial fusion, like ICF or IFE, and magnetic fusion. But yeah, we're getting to a point, actually, where the science is mature, and we can move into the engineering problem of developing a power plant. Thank you. Peter?
So, of course, from my perspective, the tool I have is a hammer, so I tend to see nails. And the biggest nail out there is fusion for the laser. So if you ask what's changed, I think, first of all, talking about laser inertial fusion, the types of lasers that are becoming available are fundamentally different from what we've seen. They are in relative terms speaking, compact, reliable, they're efficient. We have a source that makes it possible to do a net energy gain laser fusion process. So that's the first thing. Lasers are vastly different. Secondly, based on that, and in combination with the fact that there are a lot of private companies now doing this stuff, there will be really an exponential function in how many tests are taking place. Where so far it was just a few select places in the world where a few tests were taking place. Now this will proliferate. And the third is, I think, AI. I think with AI we'll have the ability to simulate, model plasma like we've never done before. And the three things in combination are a game changer, which will radically accelerate the development, at least of laser inertial fusion in my mind.
Thank you. That's really interesting. So yeah, we've got the kind of coming together, the convergence of the mature science base and the improvements in technology, both on the software side of computing, but also on the hardware side of like the laser capabilities and probably other things as well. Thank you. So what about where fusion fits into the energy market, especially when we're thinking about the fact that we have technologies already, clean energy technologies like renewables. What is the reason for still researching fusion? How important is it? Berthold, I wondered if you could tell us your thoughts from the Siemens Energy perspective. Can fusion power become a main source of reliable baseload carbon-free energy, or where does it fit with these alternative technologies?
Yeah, I mean, you're talking about a very uncertain future, so I'll talk in terms of scenarios, right? So when we look at the future market, and let's say we go out to 2050, so that's the time horizon we look at. So we do see that, and this is also coming from the latest report from the International Energy Agency, that fusion or nuclear energy in general is going to increase because global demand is going to double over the next 20, 30 years, and nuclear will also double. In terms of proportion, it is not yet clear to us, what proportion of the 10 to 12% that comes from nuclear is going to be split between fission and fusion. But nuclear will have a part to play. And I think that the uncertainty comes from how much more renewables are going to scale up, because it is also in that scenario, when you think about a low carbon or net zero, 80% of new capacity additions are going to be either wind or solar. Now, the unknown is, and also what we see today with the supply chain perspective, right, is that there is a tremendous amount of single sourcing or low sourcing on the raw materials for PV, for example. And also we see more and more challenges in terms of the scaling up of wind, especially if you go offshore. So I think that the trajectory for nuclear and specifically fusion will depend a lot on how fast, and I guess we'll talk about that in this panel, how fast we can get into demonstrators and energy power plants, because the window is going to be relatively short, right? Because the more time it takes for fusion to mature as a power source and a power technology versus a science, I think the renewables are going to have that much more time to get a bit of a head start. So we see in general it's going to be relevant. 10, 12% is what the current scenario shows. But if it really speeds up beyond that, then I think it'll depend how quickly we can get a demonstrator on the ground.
Mm-hmm. So speed is of the essence. Absolutely. We really want to be getting fusion working as soon as possible. And what are your thoughts when you were talking about nuclear technologies? I think it's probably a good idea to outline for people who may not be aware of the differences between fission and fusion, because from the fusion side, we sometimes we talk about it as fusion energy as opposed to nuclear fusion, because the risk profiles are very different. Would one of you like to talk a little bit about the difference between fission and fusion? On the academic side? Go ahead.
Oh, sure.
Constantine. Sorry to put you on the spot.
So fusion, I mean, we observe it every day. It's happening in the sun, of course. And, we're fusing, very light atoms together. Typically, the one which has the highest probability of fusing is deuterium, tritium, which are isotopes of hydrogen. It takes enormous forces to put this together, and you can have different driver technologies for that. And at the end of the day, it comes down to what the density is, what the temperature is, and the time you can actually confine it and hold it together. And so the drivers that are available are basically, magnets, and they're, because the pressure is not very high, you have to confine it for a very long time. We're talking seconds. Or milliseconds. And for lasers, the time is even shorter, but the density is a lot higher in it. And so the way this works is you take a bunch of lasers, you try to eliminate the target, which is a DT capsule, which is spherical, like the sun, for a long time. You have a shell that you ablate, that creates a pressure wave, and that compresses that because there's no way to go. So it's like a mechanical work, and so you compress it all the way to the critical densities and critical temperature, and then you start basically the fusion process. And the nice thing about this, and I mentioned the burning plasma platform, once the fusion processes start, it self-heats the plasma. And so because we get alpha particles and neutrons, the neutrons escape, but the alpha particles heat the plasma. And so it continues to actually self-heat the plasma, and so a burn wave starts propagating. And that holds together until the back pressure sets in, basically, and the thing flies out again, and the burn wave stops. And so by that, you release enormous amounts of energy, and that's how it works.
Mm-hmm. So this is the inertial confinement fusion method, or or the laser fusion method that's squashing your
It's
fuel.
not very specific on the drivers because there are multiple drivers. Lasers is one of them, but it is the inertial confinement scheme.
Mm-hmm. So there are other ways of crushing your, compressing your fuel as well. Thank you.
Yeah.
Can we ask, Tim, can you tell me a little bit about magnetic confinement fusion and how that works?
Yeah, as Konstantin said, that the conditions for fusion to happen are extreme. They happen in the sun, but the sun works because, as a friend of mine says, it's ginormous, which is beyond gigantic or enormous, I guess. To recreate that on Earth, we need to sustain temperatures of over 100 million degrees in the magnetic confinement fusion scheme. You need good insulation, and that's where the magnets come in. Basically, once you make a plasma, so you take the particles apart and they become charged, they follow magnetic fields. It's just like your house that you can either buy more insulation or better insulation. So more insulation is the strength of the magnetic field. So we go as strong as we can with the technology that we have. And this is a place where breakthroughs could happen is higher temperature fields and higher temperature operating magnets. But also it determines how large the device has to be. And so basically, the plasma has to follow the magnetic field. We shape the field and we contain at one place almost as big as this table. So within 2 meters, on my side it's 150 million degrees. On Konstantin's side it's absolute zero. And that's pretty good insulation.
Yeah, I'd say so. So yeah, you're using these magnets to really insulate your fuel, because otherwise you'd never get to the temperatures that you need, right? Because seriously, we're making like a little star here, aren't we? And so, yeah, we're making a little star. And so you're trying to get to conditions or temperatures that are like hundreds of millions of degrees, which is where fusion happens. And this actually is important because this is one reason why fusion is inherently safe, isn't it? Because it's so difficult to get these conditions in the first place. So thank you for introducing us to those. Those are the two main pathways that we use to get to fusion at the moment, and that's where most of the scientific research in the public labs has been. But increasingly, we're seeing more and more private companies now, and so these are researching different approaches or different concepts. Now, I know that both Trump and Siemens Energy have been working with a Munich-based startup called Marvel Fusion. So I wanted to ask both of you, maybe we start with Peter. Why do you think that we're seeing an increase in the number of private fusion companies, and why is Trump keen to work with them?
The first answer I think I've already given. The fact that we have these things, lasers available, and certain research results and options or potential for the future in regarding to AI. I think that's driving startups to be founded, especially in the laser fusion field. Why we're interested in it is, I guess it's quite obvious. Of course, I could now say it's for philanthropic reasons because we want to save the world. That is true too, but it's commercially, potentially, a very, very interesting field. And in my mind, what it takes to make something like this work, given this is vastly larger than anything that my company at least has ever been involved in. But what it takes is a partnership with two partners or several partners that believe in the same goal and are willing to commit to a long-term plan. And the parallel I'm drawing there, of course, is from EUV lithography, which is something it's a process to make microchips, and only one company in the world can make these machines, ASML in the Netherlands. And Trumpf has been involved with these folks from the Netherlands for the last 20 years or so, and we have together developed the driving laser behind this lithography process. And there's a lot of parallels here. Granted, what we're trying with fusion is a lot more difficult, but at least on a small scale, it's been done. A secondary source, a plasma driving laser, has been developed that can, in this case, develop X-rays that are used for chip manufacturing, and it's a multi-billion development project that we jointly did with these folks. And I feel that this type of energy and this type of collaborative effort where science-based results are used by commercial players with the goal to develop a product that in 10, 20 years could reap first benefits commercially. I think that's finally, at the end of the day, the approach that's necessary to make something like that happen. And what makes it much easier for us to get involved, I'll try to be fair with my comment, is that even if the goal isn't reached, along the way there will be so much learned about very high power lasers that regardless, it's going to be beneficial for the world and also for my company.
That's a good point as well, isn't it? It's not just about the end.
But I think
point.
that's true for a lot of players that get involved in this. If Siemens gets involved, and if other players get involved that develop certain types of steel, if people who develop cooling stuff get involved and so forth, they'll learn. And I think that should be motivation enough for a lot of them.
Yeah, it's an interesting point, because there's always like spin-offs or other things along the way. And you were talking about the commercial opportunity there, like further down the line. Do you, can you give us an idea of like what the opportunity of fusion is?
No, I mean, it's so huge. I could try to draw up numbers and say this is going to be a game changer for the laser industry. Again, I'm the laser person. But yes, if fusion came, the laser power necessary to do this and the amount of laser diodes to be produced to pump these lasers, these are laser pumped lasers that we're making for this, would be much, much larger than the combined laser industry of the world today. So this is, in any case, an easy calculation to make. But along the way, if we're just selling these things to research institutions, that already is a viable business. So that's what we're looking at this point. And we don't even try to do a business plan. Yeah. One more comment.
So you could say, in the words of Tim's colleague, it's a ginormous opportunity.
I think this is one of the fundamental problems that we, not only in fusion, but in groundbreaking technologies are facing today, that I don't know if you might have read these articles that have been published about it's harder to invent things. It was in Harvard Business Journal, I think, was an article, because science is at such a high level. I don't subscribe to that view. I think we still invent great things, but I think it takes a lot longer for fundamental new technologies to become mature. And this is a fundamental problem both for government-based and private-funded research and development, because we can't write business plans for these things anymore. And our politicians can't either for their voters. And that will make it extremely hard to finance these types of endeavors. There's going to be a complete disillusionment about fusion in 3 years' time. Everybody writes about it in the papers today and says, oh, it's going to come. Yeah, it's going to come, but not in 3 years.
No.
And then journalists will say, oh,
so you need people who can look longer term, maybe the visionary types.
Yeah. Sorry, I was much too long.
No, it's all good.
I have one more question for Vinod, by the way, later.
I wanted to put a similar question to Vinod as well, though. What about from your perspective, from Siemens Energy perspective? What do you think about the increase in private companies and the partnership possibilities or working together?
Yeah, I think Peter touched upon a lot of the why is this happening? Why is this trend evolving? So I will not comment on that. But I think from a Siemens Energy perspective, for us, there are 3 reasons why we are engaged here, right? So one is, let's talk about purpose. So as a company today, we are responsible for 1/6 of the world's electricity. We have 100,000 assets out there that are producing power. So for us, in line with this purpose, is to help our customers and societies transition to a sustainable future. So for us, if you want to be a technology company that enables that, we have to look at some long-term bets. A personal example, so there is a lot of talk today and a lot of impact today, for example, coming from 3D printing and additive manufacturing. I personally was involved in this back in 2001. Mm-hmm. And at that time, these 3D printers were half the size of this room. Mm-hmm. And so what I've also noticed is over the course of time, and that's what Peter was saying, that things take time, and great things sometimes take a long time. And that leads to the second point for us. For us as Siemens Energy, innovation is in our DNA. We have been innovating for a long time. Last month was our 175th year of existence, on the one hand. On the other hand, we are 2.5 years as a 90,000-person startup. So innovation is good for us. And working with partners like Trump and Marvel and others, our people also learn and get new perspectives that keep driving our innovation muscle. And the third is we have tremendous competencies as a company today that can help these smaller companies scale up on an industrial basis. A few years ago, we installed in Egypt, within 18 months, from scratch, 8.5 gigawatts of power. There are not many companies, and one point in that journey, we had 27,000 people working on building up these constructing these power plants. So we have a lot of experience and competencies that can be brought to bear to help this technology become real. Our expertise is not on the fusion side. Our expertise is, can we use the heat produced by this and convert that to electrical energy? So our experts are working in this team to find ways to create relatively low cost, because the levelized cost is going to be key, relatively low cost, fast installable power plants that can then use the heat from the fusion process to then generate electrical energy. So it's a combination of purpose, value, and capabilities that makes us want to be part of this.
Thank you. That's really interesting, because I think like you said, Konstantin, earlier on, it's starting to move from the science labs into the real world, if you like, and your kind of companies and these kind of partnerships is really going to be necessary to take that there. But so now I want to move on to thinking about what technological advances are still required in order to make that transition. So, Tim, can I come to you, and then I'm going to go to Konstantin as well. Like, what's still needed on the technical side?
So for the magnetic fusion side, the first one actually is generic to deuterium-tritium fusion. There's no tritium. Mm-hmm. So this has fusion fuel in it, but not all of it. And we have to close the fuel cycle. So we need the technology to make enough tritium, not just to sustain the plant, but to grow the fusion industry to be a large share.
Can you tell everyone why the fuel is in
okay, so I think most people are aware water is H2O, 2 hydrogens, 1 oxygen, but 1 out of every, I believe it's 3,000 hydrogen atoms is a deuterium atom, and that's where we can get our fuel. So nobody's going to embargo water from us. We will have it. But as I said, it isn't enough. Tritium decays after 12.5 years, so we have to make it. And we have to make enough of it we can grow the fusion economy. It doesn't exist, the capability is not here to make it, but we have the technology, at least at the prototype stage, that you can make it, each plant, so it can sustain itself. Mm-hmm. The challenge will be making enough so that you can grow. Mm-hmm. So that's one, and it's essential, and it's very specific to fusion. And so that's an area probably where industry wants to be aware and engaged, but probably won't invest because, as Peter said, there's not a lot of side benefit. Another place, which is the other extreme, as Peter said, is metals or materials. Imagine that you could make designer materials that could handle heat flux, high heat falling on it, a high rate of heat falling on it, or it stays strong at high temperature. These are both essential for fusion, but it's essential for industry. If I could sit down and design a steel for you to do whatever you wanted, I want it hard, I want it brittle, I want to be able to bend it, If we had the computational ability to do that, I think industry would bite on that. And so that's a place where I see that there's a big gain that can be made by industry, and they would be willing to invest. The final thing is magnets. For us, of course, it's very specific to magnetic fusion, but we're using superconducting magnets, and as I said, it has to be close to absolute zero. If I could make a room temperature magnet of the same size, I remove cost from the plant. As Vinona said, you have to make it able to be done and locatable anywhere. So if I can remove the complexity of the balance of plant and improve my product, then Siemens and others are going to want to have it. And we can make it easier for fusion to be, as was said, economic and adoptable. So for me, those are the big three for magnetic fusion.
Yeah, interesting. And so you talk about magnets there at the end, and we should mention that people are researching high-temperature superconductors, but for anyone who knows about superconductors, they work at very, very low temperatures, like near absolute zero. So the concept of a high-temperature superconductor is somewhat of a misnomer because they still work at like
minus 200 C, so that's not
still,
normally high.
Still
so,
pretty
but
pretty
if
cold.
We could go to
but it's still an energy
room
saving.
temperature.
Yeah, if you could go to room temperature, that would be
a real game
huge.
changer.
Yeah, but even so, I think even high temperature superconductors have a significant, like a 5-fold energy saving over conventional, and there are several startup private companies are working on the high temperature superconductors. But yeah, still could do even better. Konstantin, from your perspective, what kind of technological advances are still required?
I think he mentioned actually a lot of the commonalities already, which is then also a point to really pursuing both of these approaches. Specifically, but I was thinking if we had, high temperature or room temperature superconductors, that'd be great, because then we could actually drive the electrical power from Sahara to Europe for free. So and Siemens would be very interested in that, I think. But nevertheless, right, I think, materials, you mentioned that radiation hardening those materials. One of the big advantages, of course, of fusion power is that we don't get the zoo of radioactive products, and that talks to the toxicity of the radiation toxicity of the nuclear waste that you will still produce, but that will actually not last very long, and so you don't have all these issues which you have with fission power plants.
Can we delve into that a tiny bit? So you say the waste that's produced. What waste is produced from a fusion or from a future fusion power plant?
So I think, so first of all, you make neutrons, right? And so you have to capture those neutrons, and neutrons activate material. The difference between a fission power plant is that you get a zoo of products that come directly out of the process, and they are long life radiation products, hundreds of thousands of years. It's very difficult to manage that waste stream. On the that's fission, right? Fission. Fusion, on the other side, just basically has deuterium tritium. Tritium is a very short-lived isotope, of course, 12.5 years, I think you mentioned that. So that's not really an issue, but of course you get activation of the reactor walls and the blanket and so forth. And that is an issue, but you can design this kind of steel. So you can design it so that it doesn't activate very long products, right? And so there are a number of things, that you can try to keep out of the steel so that it actually only, activates for a short time, and then it becomes passive or cold again, as we say, right? And so we're talking about 50 to 100 years or so forth, and so that means you can recycle these power plants, which is also interesting with respect to maintaining resources and so forth. So that's the materials side of things, and I think there's huge challenges. Materials is always like a very hard research topic because it takes 10 years to make a new material and then bring it to the market. It's expensive. It's not very fulfilling, I have to say, because there are not a lot of milestones on the way there. But I think, as he said, new materials is always where innovation is born, and so that's why it's very important to invest in new materials. And it's something that we've been, I think, neglecting, and we have seen other countries actually doing a lot better than that. On the fuel cycle, yes, that is certainly something that needs to be solved. I think there's some parallels to what we're pursuing right now in the hydrogen world. And then, the third, of course, is the laser side of things, the driver side of things. And that is a completely, and Peter mentioned that before, it's a completely rethinking about how we have to approach this. This is, if you think about like these fusion power plants of a gigawatt power, so forth, they run about 15 to 20 hertz. So we're shooting targets in there, and so these targets are precision targets that need to be manufactured. And this means mass production with a precision that is incredibly high. And we've seen this before because we do this in the semiconductor business, very high precision, to optical tolerances. That is something we completely have to rethink, and it has to be cheap. The target has to be super cheap. And so we're going from something that is, on the order of hundreds of thousands of dollars right now to something that's going to be a few cents. And that is exactly economy of scale. This is something industry knows how to do. It's hard. It takes funding. It takes research, but they know how to do that. We'll see the same thing on lasers. And that is a complete change of how we think lasers right now. We have to go into optical mass production, which means we have to produce lasers like we produce cars today, but with a precision that's a lot higher. We're not looking for Spaltmaß or something like that. We're looking for, optical tolerances. We're setting the optics basically in your laser. And so we're talking completely automated production lines for lasers, and that's really rethinking how we think about this massive supply chain challenges. And that's why there are a lot of companies needs to be involved. The optics, the coatings, glass manufacturing, and so forth is really a completely rethinking. And so the last thing what it needs commitment. It needs commitment by the society and the political leaders that we really, as a society, as a country, we want this, and that's what we've seen. This is another change you're seeing right now because some countries are actually already stepping forward and making that change.
Yeah, we are, and it's interesting that you mentioned that because I wanted to move on to that. Like, does fusion need more support and funding by states? You mentioned that some countries are stepping up. I know, like in the UK at least, they've got a fusion strategy now, and they've defined their regulatory environment, which is really important. And can you tell us about what else are there other countries doing things, and what more is required from governments?
So I think, what you're seeing right now, the United States actually is with respect to laser-driven fusion, is certainly ahead because they've been investing in this for a long time for defense reasons. And so they have a good understanding basically on the surroundings and so forth. They still also have to create the innovation ecosystem where they bring together these companies, the industry, the national labs, the science, the universities, and so forth, in order to make this happen. The commitment they've given now is the White House actually put out, bold decadal vision for that. That was in March, and you see now it's being followed up with reports and funding and so forth. There's a plan how to put this together, and so you can see this is gaining momentum. We've seen this on the magnetic side, and you're better suited than me talking about that. So like the UK is one example. We're seeing also investments in fission again, like in France, for example. They put forward a program to do that. It's about $500 million in size. You see China actually stepping forward in making massive investments. But at the end of the day, I think this is such a big market, and it's such a big product challenge that we have to internationally work together, because there will be one big limit, and that's people. And unless we find enough people to actually make that leap in the amount of time that Siemens requested, we have to do this together.
Thank you. Vinod, I wonder if you could give your perspective on that. Like, what more, what does fusion need to succeed? Does it need, we've talked a little bit about it, but what do you think?
No, I think I won't repeat what Konstantin and Tim said. My general sense is that there is also a level of awareness that has to improve in many parts of the world. I think people are still looking at this whole topic of nuclear energy in a very emotional way, not necessarily in a very rational way. And that is also affecting public perception. So specifically in Germany, I think there needs to be a different discussion. And it is happening, by the way. We are having more and more discussions on how to get greater amounts of funding that are enabling or complementing the technology development from more of a product development and product demonstrator. And in order for us as a for-profit corporation, we cannot come up with a business plan that is 15 years out and expect that we will get funding for it from our investors just like that. So I think there is definitely investment needed from the government to bridge the next 10 to 15 years so that we can get to a demonstrator as quickly as possible. And then once a demonstrator is in place, then I think the market mechanics will kick in. So I think for us, it's really about trying to get, and in addition to what Konstantin said, I think it's really about working hand in hand as an ecosystem of companies to also work with the regulators to start helping shape certain regulatory policies and requirements to enable this.
Thank you. And I'm going to move to questions in just a second, but a final question to all of you, or to any of you who would like to respond. More of a call to action question. How can people listening to this support fusion? Does anyone want to?
I'll jump in with a comment and a question to Vinod. So I think what we need is more honesty in the political discussion, in the sense of that what we're claiming is true today, which means we save a little bit of energy on this side and we do a little more of wind and solar on that side, it's going to solve everything. It's not. And that's my question to you, Vinod. When you said it's ultimately a race between fusion and wind and solar, what I don't get about this is, don't we need a highly compact, clean power source, regardless of what happens with solar and wind?
Yeah.
I mean, if I look at, electrifying BASF in Ludwigshafen, we're not going to do this with solar fields and wind turbines, are we?
Yeah. No, I think there is like...
So that's the type of honesty I think we need in the discussion, so people realize we need fusion. That's the only bet we have. Unless we want fission, which is fine with me, but not in Germany. It's not going to happen. So let's be honest. But,
Yeah, no, I think it's an important point. So the way we look at it, there are three things that have to work hand in hand. So I think the first is around the production of low or zero emissions power.
Yeah.
So it's the production side. The second part that we look at is also the transport and storage of this energy, either in the form of green electrons or green molecules, because you need storage to be able to balance between the supply side and demand side of power. And the third is the consumption side, to become more efficient in reducing emissions and improving efficiency of consumption. These three have to go hand in hand. The only scenario that, and I don't think this is going to be a either-or sort of a discussion, so my only point was that there will be tremendous tailwind, no pun intended, tremendous tailwind for solar and wind to continue growing, because it is an established market today with an extremely strong cost position. Therefore, the answer to having an alternate technology will only make sense if there is a very fast reduction in cost and getting to reality in terms of demonstration, because every year that goes by to get to that, you can develop a hydrogen economy.
Okay.
And then with hydrogen coming into the equation, you don't need necessarily to have 50% nuclear. You can live with 10% nuclear around the world. And then you have hydrogen, green molecules, be it green hydrogen, green ammonia, green methanol, all of that filling in. And then you can use an existing infrastructure of gas and gas-fired power generation to run them clean.
So the race is with hydrogen.
The race becomes with storage and transport, renewables, nuclear, and then the infrastructure displacement or the infrastructure reinvestment. And I think all of these come together and you very quickly realize it is not going to be a one size or one silver bullet answer.
Okay.
No, so no one silver bullet, but a mixture of technologies, and of course we all need to deploy whatever we can as fast as we can. With that, I'd like to hand over to Adam to get some questions, please.
Yes, let's turn to our audience for questions, both our online audience, so drop your questions in the chat, and our audience here. So if anyone here has a question, please do raise your hand. Oh, we have a question just here on the right from my perspective.
Hi, Raj Apte from Google. The last conversation was really interesting. I'd like to hear from the pro case how we're going to get below 10 cents per kilowatt hour. I think the cost is really a challenge. So the cost of a combined cycle steam plant is already higher than that. You're going to need a turbine, so I don't understand the argument. Thank you.
Who would like
So the question was, how is fusion going to get below 10 cents?
per kilowatt hour. And does it need to?
Well, it does need to.
Why?
No question. But I think...
It depends what you're competing with.
We're probably the wrong panel for that. We'd have to have someone... Unfortunately, there was a person from a startup plant, but he got ill, from HB11. And they... people like that, HB11, Marvel Fusion, Focused Energy, companies like that, claim they have a path to below 10 cents per kilowatt. I tend to believe them because I want to believe them, but I'll open it to my colleagues here on the table what their view is.
I mean, I don't have a, sense in terms of what that future will look like, but for me as a energy technology provider who has to compete around the world, levelized cost of energy will be the deciding factor. Mm-hmm. And if you look at the existing technologies today, it is going to force to look at a cost target, whether we get there or not, whether we get to 10 cents or 15 cents. But if you're not in that ballpark, then it will require a very special national security sort of reason to invest in nuclear. Mm-hmm. Otherwise, the market mechanics simply will not support it. Mm-hmm. That's just my view, but I'm happy to hear from others.
I think you're making a very important point there. There has been a couple of studies actually about what the levelized cost of energy could be for a fusion power plant. One of them, which was really most complete, was the LIFE study in about 2012, I think, or 11 when we published it. And it was at that time it was about 5.8 cents per kilowatt, and so that kilowatt hours. And so this was something where we actually talked a lot with industry, and so they had a lot of input into that. Now that has to be revisited, of course. That certainly takes a lot of economy of scale projections into it. And those are very difficult to predict the future, and they're heavily affected by regulatory effects. And so I think, and what we're seeing right now, the discussion that is happening in the United States, that's happening in the UK, has already happened in the UK and in Germany, is with respect to how do we treat fusion? Is it undergoing the same regulatory that's in place for fission? And so if not, then, of course, fusion becomes a lot cheaper than, the approach to fission, right? And so I think there's a lot of these things we have to revisit. And again, that needs a commitment by policymakers and the society. And we have to have the discussion how much we want to pay for that. I think you're right about the race that's sort of like on. I don't see it as pressing, in the sense of like we're really competing right now with the solar industry, because in the long-term perspective of the world, we have a lot of emerging countries. We have, a growth to about 10.5 billion people until 2100. We have an increasing electrification of the world. So that's something that will take place. And hydrogen is always just something that we produce from cheap energy. So it always undergoes basically for storage, the efficiency hit it takes. And so at the end of the day, we're running against solar and wind. And that is a resource question. How much resources are we willing, so material resources are we willing to actually invest. And so I think this is the conversation to have. Regulatory is a strong thing. If resources become more expensive because mining of, say lithium or copper or something, which is kind of dirty, becomes more expensive, then all of a sudden, and you can see the first onsets on the development already of these raw materials becoming more expensive, then the levelized cost of energy discussion might actually turn out different.
Yeah, there's so many different things that could affect the cost. And I think it's also important to remember there have been studies as well that show that fusion does not necessarily have to compete directly with renewables, because if it's more likely to compete with gas, for example, if it's looking for some kind of firm generation in the grid. So then the studies show that fusion would only need to get to about $50 cents per kilowatt hour. So it does depend on what we are comparing or competing with. We're running out of time. Adam.
Let's try and ask a very quick, maybe binary question. We've spoken about actually different kinds of fusion. There's not one way to do fusion. Does exploring fusion in multiple different ways actually aid our search to do it, or would it be better if we're putting all our eggs in one basket?
Who'd like to take that final question? All eggs in one basket or multiple ways? I think we've covered it a little bit. Anyone?
That's a quote from Cervantes. Don't put all your eggs in one basket.
So the more we can do, the better. It's going to raise the knowledge for everybody. Thank you. I think we need to wrap up now. It's been a really interesting discussion. We've heard about advances, how fusion's made huge steps towards viability recently, and about the increase in private companies and the important partnerships that are being formed. I think it's clear that collaboration is going to be key moving forward. Fusion needs more private research and development, more results-orientated research. We need to shift from technology development to product development and systems development. We need to be making longer-term bets, as Vinod said, and we'll probably need government help to bridge to a demonstration reactor. But in general, we need to raise awareness, we need to build the ecosystem, we need to build the supply chains, we need more people coming into the field. There's a lot going on. It's going to be a very exciting next decade. Thank you so much to my panelists for joining me. Thank you, all of you in the audience here and online, for joining us today. Many thanks.